recording so no one misses anything. So, hi!
Hi.
It has been almost 2 years since I've been in a room with people. So this is new. I'm a little amped about it, but I'm also learning how to drink my Mountain Dew with the mask on, which is turning out to be challenging. Officially, for those of you who are in the classroom, we're not supposed to have drinks in here. Clearly, I am a rule follower. So just don't tell anybody. How's that? And you can have snacks too, I guess, as long as we're all cleaning up after ourselves. And of course, those of you at home, whatever goes, right? You know, you have your own house rules about where you can eat. At my house, we do not eat on the couch because crumbs are like my nemesis. And the dining room table is like 4 steps away from the couch, so it's not an imposition, but, you know, at your own house. So in terms of new stuff, I sent out an email. I had a chance to go through and look at all of your theme songs. So thank you very much for playing along with that. I sent out a link to the YouTube playlist that I curated out of those. I thought I would add my own as well. The theme song I have chosen for this semester is I must say circa 1990, LL Cool J, Mama Said Knock You Out. That is the theme song I have selected. A few know, but that is for primarily the first line of the song, which is, "Don't call it a comeback. I've been here for years." And I thought, what better way to welcome back myself to in-person teaching, right? Don't call it a comeback. We've been on Zoom for years. It's kind of the same thing. But I used to play that in high school about this time of year when I was trying to get conditioned for spring track season, to like get myself pumped up. I even put it in a dance routine in high school. Yes, I used to once upon a time. So that song is kind of like just brings me back to like that sort of simpler, happier time, so to speak. Although running outside in February or January was never a simple, happy thing, but I digress. Anyway, so we have that. I also have available now the homework system. So homework system, I'm guaranteeing, if you haven't had me before, you haven't seen this before because this is my creation. And I have a video that I recorded walking you through homework. So the way that this is going to work, homework 0 is your first homework. It is due preferably by Monday night, although there's no late points, because homework 0 is worth 2 points of extra credit. What I want to do is make sure that you all can access the system and figure out how to submit your answers before we go live with anything that actually matters. So homework 0 is a quiz about the syllabus. It should take you a good 30 seconds to complete. So if you complete it, 2 points extra credit. That's basically 2 free late homeworks. And then we will have homework 1 posted very shortly thereafter. So what I have spent the morning doing is making videos. So I have new videos up. 1 second here. I have how to get the virtual desktop working as one video. And then I recorded a video for SAS. Basically, if you've never seen SAS before, open it up and this is what everything does. How to work with it. The same thing for Stata. And I ran out of time before I got to do R. I decided to wash my hair instead. So if it were going to be Zoom, you know, that's like a dry shampoo and hope for the best kind of thing. But I thought you guys deserved clean hair. I'm making a real effort here. So R is forthcoming because I haven't gotten that far. So those are new resources available for you. And let me know if you have any problems walking through homework, if you're unable to access the system. I can fix that fairly easily on my end. So I'm trying to think if there's anything else in terms of announcements that I wanted to say. I don't think so. Any questions or comments, logistics or otherwise? No? We're good? Ready to start something new? Or new adjacent, as it were? Okay, cool. Then I have a lecture that I just finished yesterday. So it's very fresh in my mind, very close to my heart. So some of this is going to be new and some of this is going to be old. My attempt is to introduce us into the world of general linear models, slowly kind of wade in, and in the process of introducing those terms and notation systems for describing things, reviewing stuff that ostensibly you've seen before. like the idea of a null hypothesis and the idea of a significance test and what a p-value tells you and what a t-value tells you and all that stuff. So if you don't remember that right off the top of your head, this lecture is for you. And if you do remember that very well, then maybe you can multitask while we're talking. I don't know. Well, whatever you got to do is fine with me. So away we go. All right, general linear models with one predictor to start with. So a little bit of vocabulary and process first. So as we had discussed, I think last week, this is not really a statistics course, even though that's what it's called. This is a quantitative methods course. To me, the difference is whether you are learning statistics for statistics' sake or whether you view them as tools that allow you to do research using quantitative data. I view them as the latter. So the process of applying statistical models is quantitative methods, and that's what we're here to learn. So everything that I'm going to talk about presupposes that you have data already. So you don't necessarily literally have to have data, but in terms of like where in the process you would be, this is not a class that's going to talk about research design. This is not a class that's going to talk about different types of samples. There are other classes about that. Design of experiments is one that I would recommend if you want to know more about, say, between subjects designs versus within subjects designs versus mixed designs versus, quasi-experimental designs and all that kind of stuff. So I'm starting from the place that you have quantitative data, for better or worse, and you want to know what to do with it. So the steps that one would normally go through then is somehow have data, import it into software and make sure that it imported correctly. This part can be tricky, but all of the data that I'm going to give you to work with is going to be very nicely behaved so as to not emphasize that aspect. And then last week we talked about univariate descriptive statistics. So the idea of just how you describe one variable at a time. And your first homework, the first real one after this practice one, is going to be just generating descriptive statistics that you would include in a method section. That's it. It shouldn't take very long with respect to the actual analyses, because what I expect will take more time is just getting used to the system. So getting into the virtual desktop or installing R.
Do my hair while I'm in class.
Or just figuring out where the numbers show up and how to work with the code. So that process is what's new. It'll be on familiar territory. But that is important, even if you're not just doing homework in real life, to make sure that your data are collected in that column in the way that you think they are, for instance. So let's say that you run descriptives and you find out that the minimum value of one of your variables is -99. Most variables will not have a -99 as part of their metric. What that probably means is that somebody entered a code for missing data of -99 and your program does not understand that that's what that means. So anything that you would do with that variable would be wrong if the -99 is included. So that's an important step, even if you're not just doing it for pedagogy. In real life, that's my first step. Anytime I have a data set I need to work with. All right. Then the question is, what kind of model do you need? And so in this class, we're focusing on one family of models. Across the semester and towards the end, I'll sort of sprinkle in, oh, by the way, if you have this type of data, you also need this kinds of things. But this is always an iterative process. It is never the case that you have like one analysis and you're done. So the examples that I'll show you are going to be series of models, each telling you something slightly different, and you would eventually come up with a description of what happened that summarizes that process, but you often don't know what that description is going to say until you've went down the road of all of these different iterative models. And about writing. So the way that I talk is not the way that I write. So if I say things in class like, we're going to run models or run analyses, don't write that. You want to say something like, you conducted analyses or you estimated models. Running is like an informal way that I think sort of, it might rub reviewers the wrong way. So just keep that in mind, that there's a difference in how I would speak about this formally versus informally. In this room, I'm quite informal, as you may have already guessed. So vocabulary. In setting up models, which is where we're transitioning into, research questions about variables require us to designate variables as either one kind or another. And so I want to put up the list of words that you may have heard before or see in research papers and how that fits together with how I want to talk about them. So if you have a research question like, what is the role of X in explaining or predicting Y as an outcome, then here are all the words that in my head go together with X and Y. So on one side, the explainer, the predictor. In my notation, this will always be X. X sub I in particular because it's a variable that each person has an individual value for. The thing that's being explained or predicted is the outcome, is the Y. Always in my notation, I will keep that. If you want to sound fancy, an X is an exogenous variable. A Y is an endogenous variable. And the way that I remember these is X is for exogenous. Endogenous means like it's going in, something that's being predicted. If you have pictures that describe models, you might have a box that's X and a box that's Y, and if you have an arrow going from the X box to the Y box, then that would describe this same idea. Synonyms for this. So if you take design of experiments, for instance, you might hear about independent variables. And I know some of you have used that term before, yes? It's a familiar language. Zoomers, that one sounds familiar? Yep, okay. So that one has a special meaning to some people that it pertains to a variable that is manipulated or controlled. Like in a true experiment, you randomly assign people to this group or that group, and that's my independent variable. The corresponding term, if that's the way you're going to talk about it, is dependent variable. The thing you're measuring that you ostensibly created differences in because of your independent variable. Covariate is a loaded term that can mean different things. To some people, covariates are predictors. Nothing more, nothing less. To some people, in an analysis of variance independent variable, covariates are other things that you control for. Like I might have a treatment of control versus treatment groups, and I want to control for prior exposure to blah. That's a covariate. Covariates are also used to describe predictor variables that somebody cares about who is not you. So every research field has certain predictors that have to be included in a model for the results to be believable, or reviewer 3 or reviewer 2 are going to yell at you. So for instance, I used to work in the field of cognitive aging once upon a time. And in studying things like cognitive decline and physical decline and how disease and aging affect those processes, you had to control for age in all of your models or it wasn't going to work. You had to control for chronological age and then look at other things in addition to that. In certain types of settings, you might have to control for socioeconomic status, or you might have to control for, if you're looking at infants, whether or not they were born premature. Like certain things are just like, you have to control for this. Even if you don't care, that's a covariate. So to me, because those more subtle distinctions are very context specific, I'm just going to say predictor and outcome. A variable is either a predictor or it's an outcome in the models that we're looking at. How you want to pitch your story around which predictors you care about versus which ones were measured versus manipulated is a separate issue. And in regression classes, by the way, you will see this word criterion. That means outcome also. So predictor, outcome, X and Y, that's what I'm going with. So any questions on that as I attempt to drink my soda with my mask on? No? We're good? Zoomers, we're good? All right, excellent. Thanks for the thumbs. So let's practice. So here's some research questions. I want you to help me identify what's a predictor and what's an outcome according to how the question is phrased. And bonus, what kind of variable you think each might be. So to what extent does positive feedback improve performance, speed, and accuracy more than neutral feedback? The way that is worded, think about that for a minute here and tell me which is the predictor and which is the outcome. We have a question in the meantime. Why do we have to control for variables? The idea is that a lot of research questions are phrased as to whether something matters above and beyond something else that it's related to. So in social sciences, we rarely have a chance to manipulate things. All we can do is measure them. And we can't pull things apart in the way that you can if you're working with rats or plants or soil or things that are like completely controllable. So if I want to know, for instance, if mothers who smoke have infants who have negative outcomes, is smoking bad for you? Probably, but until I can randomly assign some mothers to smoke and some mothers not to smoke, I can't really say that it's causing the negative outcomes. Because then someone else is going to come along and say, well, what about people who smoke tend to be of lower SES, they tend to have less education, and those are things that are independently related to negative outcomes too. So if I really want to say it's the smoking that's bad, I have to show that that variable has a prediction to it above and beyond covariates or control variables. So a lot of times research questions are phrased as, here's this new shiny thing that no one else has looked at. I want to know if this new shiny thing contributes above and beyond all the old dirty things that the rest of the field is doing. I'm being facetious, but that's kind of how it is. You have to sell yourself as doing something that's incremental to be published. So the things that are well known in the literature to already predict your outcome would have to be covariates or controls for you to be able to show that the new thing you're bringing to the table is actually effective. So that's the answer to that question. Let me know if that didn't help. Okay, we got a thank you. So back to my other question then. What's my predictor in this question? First one here. I got one chat and one comment in the two in the chat. Positive feedback versus what?
Positive and neutral feedback.
Yeah, more than neutral. So that the way that's worded is setting this up. What kind of variable is feedback? IV. Yeah, predictor, X. Because it's the thing that's improving something else. And more than an IV, it's binary. The way this is phrased, you either received positive feedback or neutral feedback, or gave feedback of each kind. There's no other alternative. Improve performance, speed, and accuracy then. Speed and accuracy are two different outcomes. There's some task involved. I don't know what it is. A better research question would say speed and accuracy in blah, 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 and specify what they're actually doing. But yeah, those would be two different outcomes. Now, is it possible that people who take longer are more accurate because they take longer? Yeah, that's called a speed-accuracy trade-off. And if you wanted to look at the relationship between speed and accuracy at the same time that you were predicting it with positive versus negative feedback, you would actually need a multivariate model, meaning 2 Y's and 1 X. That's the class I teach before this one. We'll cover multivariate models. So with what you're learning how to do, you would be able to predict speed in one model from feedback and accuracy in another model from feedback as well. One thing to keep in mind though, speed is a variable that's likely to be positively skewed or negatively skewed. It's a callback to last week, or Tuesday. I've lost all sense of time. I don't know what day it is unless it's garbage day. Garbage day is Tuesday. So that was last week. Yeah, which way does it go?
Negatively skewed?
Which way does the tail go in response time most likely? What's the lowest response time you can have?
0.
Yeah, 0 or something in milliseconds, right? What's the longest you can take? So it's probably a positively skewed outcome. Yep, because it's named where the tail is, not where the data is. It's logically backward in how it's named. Likewise, accuracy. Is that a continuous outcome? Or is it continue-ish? Yeah, continue-ish. That's not a real word, by the way. If you put that in your paper, no one will know what to do with it. But that's my way of describing something that we're going to treat like a number and just sort of pretend like it's continuous. But in reality, accuracy is bounded on both sides, 0 or all of them. So if you have an outcome where a lot of people get everything right, you would need a different kind of model than what we're working with to be able to capture that. Okay, ready for the next one? All right, is faster academic growth in elementary school related to more frequent reading to children when in preschool?
Academic growth would be the predictor? No.
That would be the
I
outcome.
think it's frequent reading, right? Or frequent, yeah.
The frequency of preschool reading is the predictor.
Yeah, this one's a little tricky, and that's why I put the time in there. Because logically speaking, preschool comes first. If I didn't have that timing in there, it would be a little more ambiguous, I think. But yeah, in this case, faster academic growth in elementary school is sort of the outcome phrase. Related to more frequent reading while in preschool is the antecedent or the predictor. But this one is actually even more tricky than that. What specifically is the outcome?
Speed of the academic growth?
Academic growth. In what? Something.
Some reading.
It's
Some reading.
maybe it's reading. It's reading and during preschool is the predictor, but I don't know what's growing in elementary school. This is actually not a great worded question either. Now, this question, because of growth, there is a hidden predictor that's implied by the question. What kind of design would you need to see growth?
You need a pretest and a post-test.
A pretest and a post-test at a minimum, preferably more occasions than that if you want to measure change. So a hidden predictor that is implied by this question is time. Before and after, at a minimum, hopefully more than that. So
Question.
Yeah, please.
So you don't have to name the predictors, they can be hidden, but they still have to go into the tables, but they don't have to go into the question?
They are in the question implicitly, but what is,
Okay.
so this is, I'm deliberately being vague here because the translation from question to model is not always straightforward. So yeah, in order to answer this question, growth, that is a keyword that presupposes I measure people repeatedly so that I can watch them grow relative to some baseline. And that means that time has to be a predictor in the model, because I'd have to be able to say that they have more of whatever later on than they had to start with. Okay, does that make sense?
Is there ever a time in which time is not considered? I mean, I would imagine in a lot of these questions, time is almost always involved.
If it depends on the design. So the word growth, that highlights like this is a longitudinal study. If it was a cross-sectional study, let's say you have a data set where you happen to have preschool information and you happen to have elementary school information later. Then the question, if it were going to be phrased as only one observations of each, would have to be phrased differently. You would have to have something like better academic achievement during elementary school as the outcome, being predicted by reading in preschool as the predictor. So then the comparison is kids who had less reading versus more reading. It's a between persons comparison as opposed to within persons. Are you better now than you used to be, which is growth. Last one. How effective is teacher training for creating higher rates of positive feedback to the teacher's students? Now, this is another tricky one.
Teacher training be the predictor?
Yeah, I think teacher training would be the predictor. So that sort of implies that training is either a yes or no, like there might be a new program versus an old program. It could be an amount of training, so like the number of sessions or some other kind of quantitative measure of amount. Higher rates of positive feedback to a teacher's students, what's that?
I think that's the outcome, but it's related to the effectiveness. So the outcome is the effectiveness of teacher training. Because you're asking how effective is it?
Okay, can you say that again, please? Because I couldn't hear you.
I think that the outcome is the effectiveness of teacher training. So the effectiveness specifically for higher rates of positive feedback.
So in your interpretation, effectiveness of teacher training is an outcome? It could be. The way that I intended it, though, is the idea that teachers who have more training provide more positive feedback to their students. That was sort of the direction that I had intended. So how much positive feedback they provide would be the outcome in the way that I interpreted the question, but that's an equally valid interpretation. The thing that I want to point your attention to, though, is how is the outcome being measured and how is the predictor being measured? Teacher training, it's for a teacher, right? Teacher's students. So if a teacher gives a different amount of positive feedback to each of their students, then what? You would have to somehow aggregate like an average amount of feedback across the students as an outcome. But this type of question speaks to a clustered design where you have students nested in teachers, and a teacher variable would be the predictor, but a student variable would be the outcome, how much feedback they each got from their teacher. That would require what's known as a multi-level model or a mixed effects model to actually analyze that data, because students are not going to be independent if they're from the same teacher. So there's a lot of circumstances in which just predictor or outcome by itself is not as clear-cut, and it speaks back to the design that it came from to be able to fully answer the question with the models that you have. In the examples that I show you, I will be clear as to what's a predictor and what's an outcome. All right, questions, comments? Yes, in the back.
Can you clarify which models are going to be in each example?
Which models are going to be what? I'm sorry?
So each example.
Each of the examples?
For example, yes, the third example, they will gonna have multi-level model that you said.
Ideally, if you wanted to look at the outcome for each individual student, it would require a multi-level model. If you wanted to analyze it as a teacher-level model, so you could use a general linear model in that case, you would have to aggregate the responses of all the students for a teacher and create some kind of teacher composite. So a mean, for instance, a median, sometimes variability. So a standard deviation across students might be an outcome, like how inconsistent is the teacher and how they deal with their students. That could be an outcome. But the point is that you'd have to aggregate up to the teacher level on the Y side for this to be a model that is answerable with teacher, predictor, and teacher outcome. Questions from the audience. Did you all hear that question? Okay, good. I have the microphone, but I don't know how good it is for picking up. Zoomers, by the way, we can hear you in the classroom, so you can talk or you can type. Can the outcome change as you do your research? Yeah. Because I think that learning about new research designs and learning about new research models changes the questions you ask. So absolutely, this is sort of an iterative process where you think about questions in a way that you know how to answer them. You might have to learn new models to answer different kinds of questions than what you're used to. Absolutely. All right. In terms of how we're going to talk about our findings, this is a giant caveat that I have to say so that I don't get in trouble. So if I'm talking about X as a predictor and Y as an outcome, some people would get angry with me because if they're measured variables that happened at the same time, I do not have a leg to stand on in terms of which came first. Right? The research question dictates if I'm thinking of X as a predictor or an outcome, but in reality, these are just associated with each other. So in order for me to have a causal inference, like to be able to say, no, X caused Y, I would have to have X come first. X would have to be under complete control. So I'd have to have random assignment, manipulation, all that stuff. And I'd have to have a design where all other possibilities are somehow controlled for in the design or with the variables in the model. That is rarely possible in social sciences. So instead, the language that I'm going to stick to, because it's safer and more accurate, is associative language, correlational language. So if we can say that there is a relationship between these two variables, but I can't say cause, I can say things like X predicts Y, X is related to Y. If X goes up, Y is predicted to go up also. I just can't make a causal inference on that. And in situations in which you can't manipulate things, then what you're left with, rather than experimental control, is statistical control. So let's say, for example, that I'm concerned about students being able to complete my experimental task if they have a hearing impairment, because my instructions or my setup is such that they may have difficulties just because of that. I could decide that an exclusionary criteria for my study is to limit it to only students who do not have a hearing impairment. Then I have experimentally controlled for that by not allowing them to be part of my study. Or, alternatively, I could let them be in my study and I could put a predictor in the model as to whether a given student has a hearing impairment and see if it matters. And if it does matter, I would leave that predictor in the model, and then I would add the other things that I care about, and I know that those effects are not because of hearing loss, because I've already controlled for that. That is basically what we're going to do. So if you can't control for everything experimentally, you can still control for things statistically. Put the variables in the model that you think should be related, even if you can't control them, and see to what extent the things you do care about still matter after controlling for those confounding factors. That's the best we can do. So these sorts of possibilities as to whether you can say causal or whether you can only say correlational, that has only to do with design and nothing to do with statistics. If you have a design that supports causal inference, you can analyze that design with any kind of model you feel like. If you have a design that does not, you can analyze that design with any kind of model that you feel like. The way that you talk about it, though, boils down to design. So for instance, there's a class that I teach in the fall that's known as structural equation models. Have you heard of that term before? No? It's a thing. I talk about it. But a synonym for that is causal modeling. That synonym is way incorrect, because it's still just a correlation matrix that the model is operating on of variables that were measured at the same time. There's nothing special if you fit a structural equation model that somehow changes your ability to make a causal inference. So the whole like causation and correlation thing, that's basically what I'm talking about, but it's not just about correlation proper, it's about any model. So because I'm rarely in a case where I can talk about cause, if ever, I'm going to try and use words like predicts, related to, associated with, because I'm acknowledging that I really don't know which came first in data that were collected simultaneously as measured variables. Okay, so those are like my caveats. All of the asterisks in the front of the user guide, so to speak. So moving on then, one of the things that I'm guessing you would have seen in introductory stats classes is bivariate associations. Things like t-tests to look at two group differences. Things like Pearson correlation to look at how two variables are related. Things like Pearson's chi-square to do like a cross-tabulation of two grouping variables and see if there's a pattern. All of those are examples as bivariate statistics, meaning only two at a time. But most of the time, research questions involve more than two variables as part of the question, or because you have to control for all these other things in order to make your results believable. So those types of questions are best answered using predicted linear models, such as the general linear model we're going to have. And that requires us to designate predictors and outcomes. This is foreshadowing, again, about what we can and can't do this semester. We are going to be predicting outcomes that are quantitative variables that are sufficiently continuous. That's us. That's what general linear models are for. That doesn't mean that you can't predict other kinds of outcomes. If you want to do anything else, that's my other class that meets before this, that's coming back next spring. So if you need to predict a binary outcome, an ordinal outcome, a nominal outcome, a binomial outcome, a count, there are models for that, and these are the keywords that you should Google if you want to learn about those. That's why this is here. So this is just a plug that we can only do so much in one semester. If you want to predict other kinds of outcome variables that aren't continuous, you got to come back to my other class. Okay. So the phrase linear, that word means a lot of different things in different contexts, so I want to describe what it means to us. A general linear model means that the model has a form that looks like this. Constant times variable plus constant times variable plus constant times variable. It doesn't mean that we can't look at nonlinear relationships. We absolutely can. It's just that the models are all going to be phrased in this way. A truly nonlinear model would be something like y equals e to the x plus y z something, right? Like exponents, logs, stuff like that. Those are nonlinear models. So everything that we're going to do is going to have this basic form, where this part here is going to be called an intercept, and these are slopes that operate on predictors. This form also means that these predictors do not have to be quantitative variables. We can have categorical variables in here, it's just that we have to make new predictors that represent each distinct category to do so, and I'll show you how to do that. So generally speaking then, the way that these models are talked about depends on what kind of predictor variables you have. And you may have seen these terms in introductory stats classes too. Does this look familiar? A couple people are nodding in person, Zoomers. These words look familiar a little bit. If not, it's okay. So if I have only quantitative predictors of my continuous outcome, that's regression. If I have categorical predictors, that's ANOVA. If I got both, that's ANCOVA. And all of this is just the general linear model. So rather than teaching you, here's what a t-test looks like, and here's what an ANOVA looks like, and here's what a regression looks like, and here's what an ANCOVA looks like, we're going to do it all as one thing. Because it truly is one thing. The only difference is how you code your predictor variables to put them into the model. And that means that in terms of software, there is only one set of commands that you have to learn for this entire semester in each program. That's it. Everything is a general linear model that we're going to do. So stata regress, R is the LM package, and SAS GLM. Occasionally we'll look at proc reg and SAS to get standardized coefficients, but the bulk of the work will be done with one thing. So seeing this as just, here's how you predict a quantitative outcome from any combination of predictors is a much more flexible and powerful approach than trying to silo yourself into different combinations of model names based on which kind of predictor. All right. So welcome. GLM stands for General Linear Models. If I had my way, that's what this class would be called. It would not be called Intermediate Statistical Methods. It would be called General Linear Models. But I don't run the world. Someday maybe we can get some consensus on the name change. If not for that, just for better branding. Doesn't models sound more friendly than statistics?
I don't know.
I don't know. It's not better? Okay, there's some disagreement. But at a minimum, I would say that naming your class based on what you're going to cover makes more sense. Because intermediate is like, well, relative to what? Like, there's intro and then there's advanced, but what's intermediate? Like, it's one of those things that I don't think is as useful as it used to be. So what we're talking about then, univariate GLM, so predicting one outcome at a time as opposed to multivariate. And the starting point for any general linear model predicting a single outcome, which is what we're focusing on, is describing that variable. So the stuff we talked about last week, mean and variance, that's where these models start. So you're already part of the way there in understanding this. We only focus on mean and variance because these models are working with an assumption of a normal distribution for the part of the residual, the part that's left over, we'll get to that, in which there's no skewness. So here's your very first model. This right here, this little thing right here, that's it. That's not so bad, right? Just three symbols. This is what's called an empty model, because I have no predictors in it. What I have is y sub I, that's my outcome. That's my column in my data set I'm trying to predict, in which each person has their own value, that's why it gets an I. I'm going to predict that outcome from this thing right here. This is beta 0. This is my notation. It is sometimes called beta naught, but not by me. Beta 0, that's what this is called. Beta 0 does not have an I. That tells us that beta 0 is a constant. It is going to be one number estimated from our data that applies to everybody. It's a constant. E has an I. That we'll talk about on the next page. So linear models, each of these red things here, these betas, are going to have a subscript that keeps track of which one it is, starting at 0. So it'll have like beta 0, then beta 1, then beta 2, and so forth. These are known as fixed effects because they're constant. So what this actually represents numerically is our starting point to predict an outcome for any person. So just think conceptually. If you don't know anything about a person and someone says, what do you think their Y is? What would a good guess be if you don't know anything else? And feel free to read from the screen, too. This is another one where, to encourage audience participation, I have the answer in front of you. The mean, yeah. That's a pretty good guess for what someone's outcome would be, right? That's the middle, the central tendency. Not the middle value, but the average value. So let's start there. The most likely outcome for any one person, if you don't know anything else, is the mean. Beta 0 is, in this model, the mean of the outcome. That's what it indicates, because that's our starting point for our prediction. It's a naive, empty model.
Can you give an example of this? Like, it's very abstract to me in this moment.
It is very abstract. So in the examples that we were working with last time, we were looking at annual income in thousands of dollars, histogram. In that data set, the annual income on average was $17,000 and some change. So if I estimated this model to predict annual income, and I'm pretty sure that's like 2 slides from now, this number would be 17. So I'm going to predict income. What am I going to start with? Give everybody the mean. The next step after this model would be to add predictors. Okay, now how does income predict differently based on your education level, based on your job, based on da-da-da? So we're going to refine, customize this prediction. But the worst prediction that we can make in terms of like we're starting is just the mean.
Okay.
That's where we start from. Question?
So the beta 0 represents the mean.
In this
And
model, yes it does.
Yeah, and the EI so that's the mean income, and the plus EI would be, what, for example, if one person has a higher income. So does that represent that?
EI is what's going to be called the residual. I just looked at my hair. Sorry, I'm new to this whole big mask thingy. Yeah. So the rest of the slide is foreshadowing what E is going to represent, but it has an I, so you know it's for each person. So is the mean going to be the correct answer for everybody? No. It's going to be wrong at least some of the time, right? That's what E's job is. How far off are you from the mean? So E is going to be a deviation. So if I say that, for instance, my outcome variable looks like one of these figures, this is what's known as the normal distribution. If you want to sound fancy, it's a Gaussian distribution. The bell curve, yeah, that's this thing. I stole it from Wikipedia. So if I were going to estimate an empty model on each of these lines, each of these is a different variable, what would beta 0 be for the blue line? It's right here. 0. What's that thing? What's that U looking thing?
Population.
Mu, population mean. Yep. So the blue line characterizes a variable that has a mean of 0. So does the red line. So does the orange line. What makes the blue line, the red line, and the orange line different?
They're spread.
They're spread, yep.
Isn't this like the difference between kurtosis, mitosis, something like that?
It's not kurtosis.
Okay.
It's simpler than that.
Okay.
3 salient features, central tendency. What's next? You said spread.
Variance or
Variance, yeah.
Okay.
Dispersion, spread, variance, standard deviation. Put all those words together in your head. So this thing right here, you can't see it very well, but it's sigma squared, which is population variance. So the red line, the blue line, and the orange line differ in their variance. Those are the 2 parameters that characterize each of these lines. By the way, the formula for this is right here. I don't need to know that. You don't need to know that. But I wanted to show it in case you've seen it before in this context. Yes, question?
So, if one person's income is below the mean, does that the yi equals to beta 0, does that become minus after that? In that?
If somebody has an income that is below the mean, then yes, E becomes a negative number. Yep. And if somebody has more money than the mean, E is positive. So the mean plus how far off you are from the mean for each person gets you back to your variable. Does that sound familiar? The off part? You've seen this before.
Standard deviation?
Yeah, that's this. So E is called a residual. It's sometimes R instead of E, but it's also called error. Either one of those words is accurate. Error has a connotation like you screwed something up that I don't like, whereas residual just means, okay, that guess is wrong. How far off are you? So what this model is doing is giving you back the sample mean as beta 0 and the collection of deviations as these E's as variance. So another way of writing this little term in parentheses here, y sub I minus y bar, y for each person minus the sample mean. Another way of saying that is to say that it's the variance of the E's. Each person has this E residual deviation. If I square that, add it up for all the people, divide by n minus 1, I get my sample variance. So the job of this model is a naive starting point where we want to characterize what is the best guess for everybody if you don't know anything else. We know that's going to be the mean. And how much spread is there in this variable to be predicted? How much is possible to predict? The model quantifies that. It's the same thing as the sample variance at this point. But guess what's going to happen if we put in predictors? If I put in an explanatory variable to predict income, like what job you have, what should happen is that E should become smaller. How far off are you now from what's predicted? And we can measure by how much smaller by watching the variability of these E's across persons shrink as we add terms to the model. So this is very abstract, I understand. but it's a starting point. Like, what's the worst that you can do is this. Think of it this way. If you go to debt counseling, let's say that you're at the point where you have a lot of debt, you have bills coming in, you don't even open them anymore. The first thing that they will have you do in debt counseling is open the bills and figure out exactly how much you owe, right? Because then you got to make a plan as to how you pay people back and in what order. You got to know how much you owe first. I got to know how much variance there is first before I can see how much better I can do by adding other predictive information to my model. This is the worst I can do. This is all the debt. All the reasons why people differ from each other around that mean. So it's a naive baseline starting point against which we'll judge how good we do by adding other predictor variables. Okay, how are we doing?
I have a question.
Please.
In terms of like how good we do, you mean how transparent the question, like the findings were with the question? Or like how good we do? What do you mean?
How good we do, by that I mean how well are we able to predict why each person's income, for instance, is different than another person's. The best we can do is explain all of it. I know exactly why your income is what it is because I know your gender, I know your job, I know your education, I know how many kids you have, I know where you live, I know everything, right? Whatever predicts income. I'm just making shit up at this point, but the point of the story is, like, the best you can do, E would go away. There'd be nothing left that's different, that's unknown about why somebody's income is still different than what's predicted by the model, if the model is perfect. You would know all the reasons why people have a different income value. That's the best we can do. We never get there in real data. This is the worst we can do. We start from worst and work our way up. Okay. Chat says, got it. Anyone else want to ask a question? No. Okay, what's next? All right. So this is my caveat. I tried to warn you last time that at this point, it's going to be population notation for a lot of things. So betas are traditionally population slopes. In writing linear models, though, it's understood that you only have one sample. And so it's like, well, beta 0 is what we're trying to approximate. We get an estimate from our sample for it. I'll teach you how to think about how good that estimate is momentarily, but the notation that we have, the whole population versus sample thing starts to break down real quick. So you're going to see sigma squared sub E, which means residual variance in this case. At this point, it's all the variance because this is the worst model you can have because we're not predicting anything but the mean. Here's an example. I knew it was coming. One of the best compliments I ever got after I gave a talk was, it's like you knew it was coming on the next slide. And I thought, well, that's kind of a low bar if I wrote the talk, right? Like, and I'm not cheating. I don't have the PowerPoint where I can see the next slide, right? I'm trying to go from memory here as to like what I thought was a logical way to talk about this. So let's say that I fit an empty model for this outcome variable, which is annual income in thousands of dollars. This is the picture that we looked at last time. This is a distribution that is positively or negatively skewed? Positive, yep. It's the high side is where the tail is. Because you can't make less than $0. So there's always going to be a pileup if the thing you're measuring has a natural boundary. So here's an empty model. In this lecture, there is no software. Okay? There's no code. There's no output. Just the results. The example 2 PDF is how I'm going to show you the behind the scenes of where these numbers came from. But for now, I just want you to have the numbers and focus on what to do with them. How I got them, though, is coming, I promise. So here's my empty model. So if I write it generically, it's y sub I, but I can put the actual variable that's being predicted, which is income. And once I fed this variable through SAS, Stata, or R, it came back with an estimate of 17.3. That's right about here. That was the 17. I was close. So the average person in this sample, which is from the General Social Survey of 2012, I selected a subset of that data to build this example, makes $17,300 on average. Clearly, some people make more, some people make less. So E for each person would be calculated as what is your actual income, that's indicated by the Y, minus the income that the model predicts for you, which is the mean. What we care about, though, in terms of interpreting our results is not the individual E values. They are a means to an end. What we want to do is collect them and talk about their spread, their dispersion, their variance. So the model output is also going to give us a number that corresponds to the variance of these E residuals. How far off is each person from the mean predicted by beta 0? Square that, sum it, divide by n minus 1. That's where the 190 comes from. And if I take the square root of 190, that is my standard deviation of the E's, and that's 13.8. So on average, people make $17,300. But the average deviation from that average is $13,000. Now, why is there this much variability? I don't know yet. I just know that I have this much to predict. So conceptually, this 190 is all the reasons why some people have more money than others. That's it. It's a number that corresponds to that idea. Okay, with me so far?
Mm-hmm.
So next question then. Okay, so it's 17. Now what? I'm supposed to be, in theory, collecting a sample of data so that I can make some kind of conclusion about how income functions in the general population. So if my sample mean here, 17.3, is supposed to be an estimate of the population mean, how good of an estimate is it? That's a different question. So do any of you play card games that involve bidding? Like hearts? No? 10-point pitch? A couple of you are nodding. What do you play? Video card games?
Euchre and spades.
Spades? And what was the first one?
Euchre.
Euchre? Okay, I don't know that one. Zoomers? Any card games that involve bidding for points? No? Okay. Yeah? What do you have?
Spades too, and we call it pepper.
Spades and what? I'm sorry?
Pepper?
Pepper? Okay. So there are many card games in which the object of the game is to collect points. And you decide like what suit you're going to play in or what cards you're going to play in. At my house, it's 10-point pitch or 13-point pitch, which is a Nebraska thing. I'll explain it to anyone who's interested. But this is what you do at Thanksgiving if you live in Nebraska. It is required. So in pitch, it's a 4-person game, and you go around the table and you bid as to how many points you think you can get. And at my house, if you know the family members, the way they say their bid is a tell, because you might get 7 or 4, 6. Like, I want the bid, but I'm really not very sure of myself right now. 6? So what I'm asking here, it's like, the mean is 17, or is it, I don't know, like 17 or something? Like, how good is that number? Another way of saying that same question is, okay, so what if I grab another sample? I have the General Social Survey from 2012. What if I do it again in 2013? What if I do it again in 2014? Am I going to get 17 every time?
No.
No, probably not. But how different is it going to be? Is it going to vary a lot? Like any one sample is not very trustworthy, or is it just going to kind of wiggle a little bit such that it's like, well, it's 17, close enough. It's 17. So we need something else to quantify how good 17 is as an estimate of the mean, how believable it is from just this one sample. So we need to quantify a new term for you. You may not have heard this before, a sampling distribution for the mean. Is that a term you've heard? A few people have. Zoomers, a few people have ish. Now this is, to me, this is a very difficult concept to get for the first time because it's so different. Like if I look at this distribution right here, these are people. They're grouped into bins of $500 based on how I made this, but like each person's in this is a description of my variable in my data set. A sampling distribution is not this. It is a higher level of abstraction. So to demonstrate this, I'm going to make up some data. Believe it or not, quantitative methodologists like myself, this is how we do research. We make up data with our computer where we know what the right answer is, and then we test different models or different approaches to see how they get the right answer or not, and then we write papers about which ones work best. That's quantitative simulation research. I know that you're like, oh my God, I totally picked right. I do not want to do that for a living. But I gotta tell you, fake people, very well behaved. You can also get tons of them without paying them. So I made 100,000 fake people, and I lost a zero here. It's 100,000. I'll fix that afterwards. And I simulated one variable with a mean of 10 and a variance of 25. And here's the histogram that I got back. And the blue line is what it was supposed to be, and the red line is what I ended up with. And the fact that you can't tell them apart illustrates that, yeah, it worked. So I have 100,000 people, and they collectively have a mean of 10 and a population variance of 25. So any one person in this fake data set of 100,000 people is off from the mean by 5 on average. Okay, with me? So this is mimicking like the idea of a population. I can make one that's fake. In reality, we never actually know what it is. So then what I did to make this picture is sample from it. So I told the computer, go grab me a sample of 5 people. Go grab me another sample of 5 people. Go grab me another sample of 5 people. And I did that 1,000 times. And then I said, now go grab me a sample of 10 people. Go grab me another sample, another sample, another sample. And I did that for 5 people in each sample, 10, 15, 20, 30, and 50. What you're looking at here are sampling distributions. These are not people. What you are looking at is a histogram that characterizes what the sample mean was out of each of these subsamples that I grabbed 5 at a time, 10 at a time, 15 at a time, and so forth. So if I only have 5 people in my sample, the right answer here is indicated by the gray line. What I get back for the mean is hella noisy, to use a technical term. It's anywhere from like 5 up to 15 when the right answer is 10. So this depicts how inconsistent the mean turns out to be if you only have 5 people to estimate it in any one sample. If I got 10 people, still hella noisy, slightly better. 15 people, okay, it's calming down a little bit. By the time I get to 50, yeah, I'm pretty much right on. There's very few cases that are outside, say, a mean of like 8 versus 12. So the more people that you have in your sample, the tighter your distribution of what that mean turns out to be in each sample is, the less inconsistency you would have across samples of that kind. These are not people. These are samples. These are sampling distributions. What happens then? Oh my goodness. I have a picture here that like looks very different, but anywho, it's supposed to be that picture. I calculated what the standard deviation is, and that's on this right here.
I mean, it's normal on ours.
I know, it's looked normal on my PDF too. I have no idea why it just decided not to do this, but I want this table right here. That's what I want to point out. So I calculated what the standard deviation is of these distributions. So this is not the standard deviation from before. This is a different standard deviation. And this is where it gets really like hard to conceptualize the difference. And that's why I'm trying to make pictures. The standard deviation of this distribution talks about how far off any one sample mean is from the right answer is supposed to be in the population. The standard deviation is in this column right here on slide 14. It gets smaller, tighter, less dispersed, more consistent as you get more people in your sample. What about if I have more variability? How should that affect how good of an estimate my mean is? Well, let's see what happens. So I got a new set of fake people, and I set it up so that their population variance is 9 instead of 25, with a standard deviation of 3 instead of 5. So here on the left is what I had before. Here on the right is my new people. Okay, now it's going to cooperate, thank goodness. So the same thing is true, that as you get more people, it gets tighter and more consistent. The standard deviation decreases. Now let's compare standard deviation of 5 versus 3 on slide 17. So the difference between the top row and the bottom row is how much variability there is across people in each of these samples. So in addition to your sample mean being closer to what it's supposed to be the more people you have, your sample mean is closer to what it's supposed to be the less variance you have across your people. Which makes sense, because if everybody's really different from each other, then you would expect your mean to like move around all over the place based on who you happen to have in your sample. Whereas if everybody's somewhat the same, then your mean's going to move less. So in these sampling distributions, these are characterizing the behavior of a mean across repeated samples. It is a summary of the people, but the people are not part of this. So two things affect whether the mean of income is 17 or is 17, how many people I have to get the 17 from, and how variable they are around that 17. So it turns out that I don't have to play God and make up fake people to figure out how good of an estimate my 17 is. People who are way smarter and know way more math than me have already done it for me. Even though you only have one sample, you can still figure out how good of an estimate that one result is for your mean in particular, which is what we're talking about here, with something called the standard error of the mean. That sound familiar? That's one of the first things that you get taught. What it is a proxy for the standard deviation of the sampling distribution of the mean. Standard error of the mean has two ingredients: sigma or sigma squared, depending on the form here, meaning how variable are the people in your sample from one another, and n. What's n again?
Population.
Total number of people.
Number of people. So as n goes up, the denominator gets smaller, standard error gets smaller. As standard deviation goes up, it gets bigger. And in practice, we never know what the population standard deviation is, so we throw in the sample one. So here's why this is confusing. Here's the generic definition of this. I have an example on the next slide that might help. So I've got two words, standard deviation and standard error, that sound a lot the same, but they're talking about different things. So first up is standard deviation. That's my 13 from before. If I'm talking about a standard deviation of a variable, I'm talking about this. How different people in my sample are from one another, the spread. The fact that the standard deviation is 13 That is telling me that on average, any one person's income is off from my mean of 17 by 13 on average. The new thing that I'm trying to describe standard error, it's computed using these data as 0.51. The standard error is not about the people, it is about the samples. What a standard error tells us is how far off on average any one sample's result is expected to be relative to the population true value. If I redid my study, how wiggly is my mean going to be? Well, it's going to be off by 0.51 on average. That's what this is telling me. So now I have a way to quantify if the mean is 17 or 17. If I had a standard error of 0.5, that means, yeah, like it's going to be somewhere around, I don't know, 16 to 18, pretty tight, versus if my standard error were 5, then it'd be more like, yeah, it's 17 in this data set, but it could be anywhere from like 7 to 30, I don't know. .313. I'm all worked up and now it's time to go. So it's a hard concept because it's a level of abstraction that's higher. You're talking about what would happen if you redid your study over and over and over again, even though you only have your one study to go off of. It turns out that it works. So here is the standard deviation of these sampling distributions that I computed with my known fake people, and here's what the standard error would be on average. It works. It's amazing. Math is cool when someone else does it for you. Am I right or am I right?
You're right.
Yeah. Okay. Questions before we call it a day?
So you said, like, for example, if the SD is 13, you can say that it is 17 minus 30 for the income, if the mean income is 17. But I have a question. Is the value of SD a representative of is that the number of the mean, or is variance the same value as the mean?
So question on mean versus standard deviation versus variance, is that what you want to clarify?
Yeah, like, can you do 17 minus 13 based on SD, or do you do like a 17,000 minus 190?
So it depends on what you're trying to talk about. If you want to know, okay, so how good of an estimate is 17 for any one person in my sample? And be like, well, it's actually not great, because on average, any one person's going to be off by 13. So that's like a lot of wiggle around 17. But standard error is a different question. If I got another sample of people, am I going to get 17 back again? No. How far off am I going to be? Oh, it's going to be off by 0.51 on average. So that there are two different ways of talking about dispersion, but it's dispersion of what? Standard deviation is dispersion of the people you have. Standard error is a predicted dispersion of what the results you got across hypothetical additional samples of the same kind. I know. It's a lot.
Lisa?
All right. So yes, last question.
Yes. So how does the standard of error help in utilizing or choosing the population that you want to work with when you're doing a study?
How does it help in visualizing? Is that the question?
No, I was asking how does the standard of error help in choosing the sample that you want to work with?
It doesn't, because you won't know what the standard error is until you have a sample to estimate it with. But what it can tell you is how predictable, like, another sample is going to be. So it's like, how consistent is this across if I did the same thing over and over again? That's what it tells you.
Makes sense.
All right, so it's Thursday because it's not garbage day, which means I say see you next week. Have good weekends. Take care. Thank you for coming.
Thank you.
Office hours today are going to end at 4, by the way, because I have to get my computer fixed.
Okay.
So if you want to talk to me, now is a great time. I'll just hang out on Zoom and in person. Bye, folks.
Question about beginning homework.